Okay, hello everyone. Let's get started. So last time, what we did was NTK, the neural tangent kernel approach, and so today we're going to continue with that to finish the last part of the neural tangent kernel approach, and then we talk about the so-called implicit regularization effect. So last time, briefly, we recall that last time we have done the following. So we have claimed that there are three steps in this analysis using the NTK approach. So one step is that you say, that f theta x is close to g theta x in some neighborhood. Oh, wait. Oh, sorry. Yeah, there are too many steps in this setup, so I always forgot some step. The worst step I would forget is I forgot to record all. Then like other, this one you can remind me, but if I forgot to record, then nobody would remind me. So that's the thing I check every time. Okay, cool. And I think this is recording. This is recording, and you can hear me on Zoom, right? Maybe it's
Zoom is cool. If it's recording, we can hear you.
That would be great. Nobody seems to say anything, but it sounds like it's recording. It's receiving audio. Okay. So let's. So last time we said that if in some neighborhood theta around b theta 0, you can have accurate approximation. And recall that the b theta 0 was something like a neighborhood of size, something that depends on the sigma. So b theta 0 was defined. We show that if you look at the neighborhood where you have some state where theta is close to theta 0 with distance something like square root n over sigma, then you indeed have something. I guess you get how well the approximation is. I think the approximation in this neighborhood, the approximation error is something like beta square root n, beta n over sigma square. Right, that's what we had. And also in this neighborhood, in this neighborhood, so there exists a global minimum. With error 0. Nobody seems to respond to my request about confirming that the audio is working, but I don't know. There are only 4 people here. Oh, okay. Oh, okay. So you can hear me. Okay, thank you so much. Great, thanks. It's just sometimes I get paranoid by this. Okay, thank you so much. Okay, cool. So, all right. So this is what we proved last time, and we discussed, this quantity is the key thing, right? Beta over sigma square is the very key thing. And if it goes to 0, then that's great, because your error becomes smaller and smaller. Oh, I see. I cannot hear you. That's the problem. I see. Probably now I can hear you. I think my speaker is the volume is very low. Okay, cool. Thanks so much. And now the third step, as we discussed last time, is that, and we have discussed various cases where this beta sigma square is goes to 0. We discussed 2 cases. And today we are gonna talk about the third step, where we show that optimizing with f theta with a neural network is similar to optimizing with g theta. And in some sense, the only thing you care about is an analysis of the optimization for f theta, but you want to do this kind of like relationship so that you can make the optimization easier. And we also briefly discussed, what we do with this optimization. I think there are two ways. Right? One way is there are two ways to deal with the g theta. So I think there are two ways. One is something like using strong convexity, and the other is using only the smoothness. And today we're going to focus on this case, which doesn't require too much of the background about optimization. All right, so now let's go into the detail. So by the way, I think a small remark before I go into the detail. So why you care about the step 3 in some sense, right? So a priori, there's no reason, okay, so there's one reason, which is that you want to understand what happens when you optimize over neural networks, right? But suppose the solution, the understanding, suppose at some point, like we are at a moment where we want to prove this number 3, but we haven't succeeded, right? You probably would question yourself, why I care about such an answer, right? Even I prove this answer, why it's interesting? And the answer is, yes, it's not that interesting because if you prove that optimizing over neural network is the same as optimizing some linear model, right, like a kernel method, then why not just using kernel method, right? And it turns out that that's indeed true. Like if you use kernel method, it's not going to work. If you optimize neural network in this way, in this particular initialization, with this particular learning rate, so on and so forth, it wouldn't work as well either. So in some sense, this is so this whole theorem, the value of this theorem is only for showing that under certain regime, optimizing over neural network is the same as optimizing over linear model, but there's no any like bigger impact in some sense. Like just because you are optimizing the neural network in a weird regime, which is the same as optimizing kernels, and in this regime, nothing works very well. But still, for the technical reason, let's still try to go through this. It's not super complicated, and I think in some sense the techniques is kind of useful because partly because I think it's somewhat surprising because at the first place you wouldn't probably believe it, right? Why you believe that optimizing neural network in any case would be similar to optimizing kernels, and this shows that that's possible in some cases, even though that case is not that informative or that kind of like useful. Okay, so. Let's analyze. So we start with, the first step. We start with like analyzing the optimization with g theta. So, and this is really just a linear regression, right? It's really understanding optimization of linear regression. So the problem is really you take mean of this y vec minus phi delta theta 2 norm square with GD. And just to briefly recall the notation, so phi is this feature matrix, which is of dimension n by p. So this is n by p matrix, and each row is something like grad f theta at 0 x I transpose, let's say. You put all of these as rows. What exactly this phi matrix is, doesn't matter so much anymore for the rest of the discussion because phi is just a matrix. And delta theta is the difference between theta and theta 0. And we are just optimizing over delta theta. And what you do is we just take gradient descent, and you'd say then the gradient descent is you take the gradient, and the gradient is phi transpose times y vec minus phi delta theta. Right, this is the gradient update. And one of the kind of the features of this analysis is that you are looking at the convergence, the changes in the output space. And in some sense, this is kind of like, to some extent, this is the spirit of the kernel method, right? You're looking at not the parameter. You don't look at the parameter space, but you look at the output space. And when you look at the output space, it's kind of like you're looking at the function space to some extent. But what does that mean? That means that you're looking at the output y at time t plus 1. So this is defined to be just the phi times delta theta at t plus 1. I guess by definition, let's define the version with t. So, and you look at how you change the residual over time, right? So you compare your output at time t with the target output at target output y vac. And how does this change over time? And this is just the definition. And you plug in the definition of theta t, which is delta theta t minus eta phi transpose y vac minus phi delta theta minus y vac. And now this, requires some kind of like rearrangement to make it look cleaner. And how do I rearrange this? I guess I'm going to first group everything about delta theta. So you group this term and term related to this. This is also delta theta t. So you get phi minus eta phi transpose phi. I think I'm missing something here. What's wrong with this? One moment, sorry. Yeah, okay, I think I'm right. So if you look at what's multiplied in front of this term, there's this one and this one, right? So there are three things multiplied in front of the theta t. So this is the multiplier in front of theta t, and then you look at the multiplier in front of y vac, then you get minus eta phi transpose plus identity y vac. And interestingly, this you can write it as I minus eta phi transpose. Sorry, phi. I can write this as eta phi transpose times phi delta theta t minus I minus eta phi transpose y vac. And then you get I minus eta phi transpose delta theta t minus y vac. All of these are basically just a standard calculation. I think some version of, if you take some version of like a linear regression course, then probably you have seen this. You get this. So that's the update. That's the recursion for the residual of the output. And you can see what happens is basically the residual in the previous round got multiplied by this matrix. And what this matrix is a matrix that is smaller than identity because you have I minus something. And this something is a PSD matrix. So you are shrinking your residual in some way every time. So, and you can quantify how fast you are shrinking. So when eta is less than, say, 2 over sigma max phi transpose, and let's define this quantity, let's call it 1 over 2 tau square, then you can show that this convergence, then I minus eta phi transpose can be shown to have operator norm less than 1 over eta tau eta. So I think I have some eta sigma square. So, and then you have, okay, so this, I'll show this in a moment, but suppose you have this, then you know that y high t minus y vec in 2 norm is less than the operator norm of this matrix times, sorry, let's take this t plus 1, y vec 2 norm. So this is less than 1 minus eta sigma square, y hat t minus y 2 norm. And this is, if you do a lot of recursions, you get 1 minus eta sigma square to the power t plus 1 times y vec 0 minus y 2 norm. So you have an exponential decay of error. Yeah, yes, that's a good point. So sigma is the minimum value of phi, and let's prove this right now. So this, let's say this is number 1, but suppose you have number 1, then you have all of this exponential decay. Right? So now let's prove the number 1. So how do we do that? So establishing 1. So intuitively, it's just really that this is a matrix as PSD, so that's why you subtract something, right? Your operator norm is less than 1. No, right? So, but we need to make sure we know exactly how small it is, right? It cannot be, if it has to be strictly less than 1. That's why we needed this equality 1. And to see this, I guess, you know, there are multiple ways to see it, but I think the way I tend to think about it is that, so first of all, sigma is sigma mean of phi, which is also the sigma mean of phi transpose square root. This is just by the standard property of the singular values. So so I guess, you know, one way to think about this is that if you look at the either eigenvalue or singular value, because this is a PSD matrix, so it doesn't matter, value of phi transpose, then let's say, suppose the eigenvalues are tau 1 square up to tau n square. And then tau 1 square is equals to tau square. That's my definition of the sigma max, right? And tau n square is the sigma square. This is my definition of the sigma mean. And then the I minus, we care about this matrix. So this one has singular value, eigenvalue or singular value. 1 minus eta tau 1 square up to 1 minus eta tau n square. Right? This is just because I has singular value 1, so I'm not sure whether this is, do you think this requires a proof? This is just because, I guess, there are many ways to see this. For example, I guess the best way for me to see it is always I take eigen decomposition. You say phi is U sigma V transpose, where sigma is this matrix with tau 1 up to tau n, and then I minus phi transpose, eta transpose is just I minus eta U sigma square U transpose, right? And I is equals to U transpose, and then you get U times I minus eta sigma square U transpose, and this is the SVD for, or the eigen decomposition or SVD for I minus eta phi transpose. And that's why what's inside is the eigenvalues or the singular values for the resulting matrix. Right. So and then now you bound this, right? So they are, but if you care about the operator norm, you care about the largest, the absolute value of the eigenvalue, right? So basically that's why I minus eta phi transpose, the operator norm is less than the max over j, 1 minus eta tau j square absolute value. And I think your eta is guaranteed, the choice of eta is trying to guarantee that you never get to the negative side. You try to make sure the eta is less than 1 over 2 tau square, and tau is the largest one. So that's why even the largest one is, even the largest tau will not make the 1 minus eta tau square negative. So everything is positive. So then this is just equals to 1 minus eta tau n square, which is equals to 1 minus eta sigma square. Okay, so sounds good. Yeah, in some sense, these are, in some sense, the basics of optimization. But this course doesn't require optimization. That's why I'm providing some basic tools here. So right. So okay. So basically, we are done with the analysis of this linear regression, right? After you have this, you know that your error is decaying exponentially fast, and then after sufficient number of iterations, your error is small, right? So basically, maybe let's call this 2. So from 2, you have after for t is at most something like log 1 over epsilon over eta sigma square iteration. So your error y hat t minus y vec is less than epsilon times the initial thing. And you can take epsilon to be small so that you can have a, you can take epsilon to be very small, right? Because it's a logarithmic decay of errors. Okay, so this is analysis for G, and now let's talk about analysis for F, right? So you'll see that the analysis for F is very similar to this, just with some tweak. Maybe let me state the theorem just so that we have a formal statement somewhere. So there exists a constant, say C0 and 0 and 1, such that when this key quantity beta over sigma square is less than C0, for sufficiently small eta, and eta this could depend on, which could depend on beta, sigma, maybe the dimension p, so on and so forth. I think you can have a concrete bound for how small eta has to be, but I'm just lazy. I want to, not I'm lazy, but like I want to hide these details. I'm also lazy, but I also want to hide these details so that it's not too complicated for the expression. But when you have sufficient small eta, then in t is equals to O of log 1 over epsilon over eta sigma square steps, the empirical loss for the f theta t is also less than epsilon. So the empirical loss for the neural network is also having this error epsilon. So how do we do this? So I guess we have kind of discussed the intuition already. So the intuition is that you always have try to kind of relate this to the G. So, and here by relating to the G, basically you just try to follow. What I mean is really you try to follow the proof you had before. Like just try to imitate as much as possible. And of course there will be some differences, and then you deal with the differences. So I think one difference is that, by the way, this is a proof sketch because I'm going to omit some small technical jargons, which is not super important. So the important thing is that you have a changing phi in some sense. So this is what the difference in neural networks when you have neural networks compared to the linear regression case. So you'll see why this is the case. So suppose you define this phi superscript t to be the kernel at time t. Right, so this is the NTK kernel when you Taylor expand at time t. And if you Taylor expand time t, then then the gradient descent, I think we have discussed this before, but now you can see it explicitly. I think I have claimed that if you tail expand at time t, then the gradient with respect to the approximation is the same as the gradient with respect to the original form, the neural network, right? So this is what I think wrote at the very end here. This is a remark. So if you tail expand at time t, then the gradient with respect to neural network is the same as the gradient with respect to linear function. This is just because these two things agree. These two things agree at this point up to first order. So that's why even you compose with a loss function up to first order, they still agree. So, and here you can even see that explicitly. So suppose you write out the gradient of the loss function at h theta t, then what you get is that you have 1 over n. You can do the chain rule, so you can get this is yi minus f theta t xi times gradient f theta t times xi. You can verify this just even without using the remark I had, right? This is just a chain rule, and then this is equals to if you view this as this is from the phi. This is the ith row of the phi, right? So this corresponds to ith row phi, and this corresponds to the difference of. Maybe let me write this more explicitly. This is yi minus yit, right, times the gradient. And then if you write this as a vector for matrix multiplication form, you get phi t, which corresponds to this one. And then you have y vec minus y hat t. And there's a 1 over n in front of it. Right. So that's the gradient. And that means that the update rule for theta t, I think I somehow wrote theta t. Yeah, up rule for delta theta t. I guess I'm going to use theta t instead of delta theta t. They are the same, right? They are just only different up to a translation. So theta t plus 1 is equals to theta t minus eta times this gradient. And this is equals to theta t minus 1 over n times phi t, y vec, y hat t. And okay, so now there is a little bit kind of like small thing here. So suppose you say you give a name called this bt. So then this is, let's say, eta 1 over n. So this is theta t eta bt. So I'm going to try to okay, so what's our goal? Our goal is try to get a recursion for the y's. That's what we did before, right? A recursion for the y's. And how do I get a recursion for the y's? I have to look at how the y changes, right? What is the y? This is one entry of the y hat. The output at time t plus 1. But I want to write this as something like related to the time at time the function output at time t. So how do I do that? This is a nonlinear function. Before we just do a linear multiplication, because before we just know that if this is g, if this were g, then this is just equals to phi times delta theta t plus 1, right? If this f was g, but because this is nonlinear, we have to do something. So what we do is we try to Taylor expand at time t, so that you can have a relationship between theta t and theta t plus 1. So if you Taylor expand, then you have to write the gradient of f theta t xi and times the differences between the two iterate and plus something high order, right? And if you look at what's the difference is a function of eta, right? The difference is exactly this eta bt. So that's why we can write plus the gradient at theta txi times minus eta bt, and plus the second order term will be a quadratic in the, this will be a quadratic in this way. If I'm going to write it somewhat informally and more formally, I can write this as something, a function of like eta squared times something. Because the difference has a eta in it. So that's why you square it, you get eta squared. So in some sense, this is a term I want to ignore. I'm trying very hard here just because I want to ignore this term. And the reason why I want to ignore it is because it's eta squared, right? So basically what I'm going to say is that mt, the constant, is not a function of eta. So if you fix everything else and just take eta to be very small, so if you take eta to go to 0, then the second order term, the eta squared mt term, is negligible. We can do this more formally, but I don't want to go into so much jargons. But there's a way for you to kind of bound mt by something, right? Whatever you bond it, right? So you get a bound for mt, and then you just say that if eta is small enough so that eta squared of mt becomes negligible. That's basically how you formally do it. So if you ignore this second order term, then everything becomes so simple, right? So for now, let's ignore the second order term. Then what you have is that y hat t plus 1, this is equals to, if you put this equation, let's call this equation 3, in vector form, then you get y hat t plus 1 is equals to y hat t, because this is y hat t, and plus this linear function of bt, right? So what is this? This is really eta minus eta times phi transpose times bt. I guess actually this is right. So yes, phi transpose times bt, and then plus something like eta squared times some constant. I'm going to keep this just for a little bit so that, but essentially I want to ignore it, and then you can rewrite this as y hat t minus eta phi transpose. And what is bt? bt is this difference between theta t and theta t prime. Is this something like this? Right. Let's go back to that. So this phi. Wait, I'm not sure why I'm missing I have a constant here. Oh, I see. So I think this 1 over n. I guess there's some mismatch in my notes, but it doesn't matter. So let's have the 1 over n here. Well, for the linear regression case, I didn't have the 1 over n in the loss function, and now I have the 1 over n. That's why it's a little bit mismatch. But it's not a fundamental difference. So so let's have the 1 over n. Then you have this is phi t. Sorry, this is phi t. And then you have eta phi t transpose times y vec minus y hat t times 1 over n. Maybe let me, okay, how do I do this? So let me ignore the 1 over n forever, because you can redefine a loss function whatever you want, right? Like let's say just we don't have 1 over n in a loss function. Sorry. So so then you have this, and then this becomes if you subtract y vec from both of this, and then you reorganize this. So you're gonna get this is equals to I minus eta phi t transpose y hat t minus y vec. I think there's somehow there is a little bit problem with the there's a little bit. I think this is a plus. This is a plus, right? Okay, but the point is that basically if you compare this equation, I guess technically you still have some eta squared term, which we don't care. If you compare this equation with the recursion before, the recursion before was this. Actually, maybe here. The only difference is that this matrix is different. Right? Before you are multiplying with a fixed matrix phi transpose, and now you are using phi t transpose. But everything could be the same if this phi t, but you don't necessarily need it to be the same, right? In the original proof, you only need this matrix to be smaller. You only need I minus eta phi transpose this matrix to be smaller than identity, right? So suppose we ignore the eta square m term because it's second order, and then suppose theta t minus theta 0. Suppose you are within sigma for a beta at time t. Then suppose you are not very far away from the theta 0. Okay, so then you know that phi t minus phi in 2 norm is less than sigma over 4. This is by Lipschitzness of phi. This is our assumption. And that means that sigma mean of phi t is not very different from the sigma mean of phi. Say minus sigma over 4. This is larger than 3, 4 times sigma. So sigma mean of phi t is also good. So the eigenvalue, so you still have a lower bound for the eigenvalue. It's just a little bit weaker, up to a constant factor. And that means that I minus eta phi t transpose operator norm is less than 1 minus eta times 3 over 4 times sigma. Right, so very similar to the before. And then, but there is an assumption here. So this sounds great, right? But there is an assumption which is that theta t is not very far away from theta 0. This is something you cannot take for granted. You have to prove it is the case. So that's why we have to inductively. So basically, the only thing left is that we need to inductively prove this. Prove theta t minus theta 0 is never too big. That's basically that's the thing, and in some sense this is expected because you need this is expected because in some sense this is expected because recall that delta theta hat, the 2 norm, theta hat was the global minimizer. This is the global mean that we constructed in the last lecture. So we said that there is a global mean of size square root n over sigma, right? So and because there's a global mean with this size, and if this is much less than sigma over 4 beta, right? So when sigma beta over sigma square is sufficiently small, right? So I guess this, when beta over sigma square is sufficiently small, then you have this equality. And that means that there exists a global mean within this region sigma over 4 beta. If there exists a global mean within this region, why you should leave this region, right? That's why you should somewhat expect that it's always within this region. And how do we formally do this? I think you just say formally, you just do an induction, right? Because you know that, I guess square root, we know that 1 over n, let me see whether I made a mistake here. So 1 over square root n times y hat t minus y vec. 0, this is O of 1, because every entry is on the order of O of 1, so you have n entries. So and then inductively you can show that, this implies that we actually have exponential decay of error, but actually even you don't care about that, you still have, for every time t you have this. And if for every time t you have this, then it means that our square root n phi sigma t minus sigma hat 2 norm is less than O of 1, because theta hat is the ground truth, right? So this is because phi theta hat is equals to y back. Theta hat is the construct, the one that we constructed last lecture. And then this means that theta t minus theta hat 2 norm is less than square root n over sigma, which is expected, right? You are saying that your iterate is not very far away from your target theta hat. And then you also know that your target theta hat is also not very far away from. So we also know that the target, this is also less than, I guess there's a big O here, big O of square root n over sigma, because this is what we did last time. And then by triangle inequality, we get theta t minus theta 0 is less than theta t minus theta hat, theta t minus theta hat and theta hat minus theta 0 to a norm which is less than O square root n sigma. And this is less than sigma over 4 beta if beta over sigma squared is less than, much less than 1 over square root n. So this is how you inductively maintain the distance between theta. How do you inductively show that theta t is not very far away from theta 0? Yeah, the step sounds a little bit complicated, but actually the intuition is very simple. It's just that there are probably many ways to prove this. Like I just present one way. So like there's already a global minima there, right? So there shouldn't be any ways for you to leave. And what you do is basically you say that you have a theta hat here, you have theta 0. You know that these two are, the distance between these two is of square root n over sigma, and you are optimizing, and in some sense theta hat is your target, right? Because theta hat has the best fitting. So you're somewhat moving even closer to theta hat. So why not? You should have even bigger distance eventually afterwards, right? So that's why this is working, right? So if you look at the iterate, I think you are somewhat moving to theta hat. So okay, so and out of all of this, right? So then we got this equality. And with this equality, we get that y vec t plus 1 minus y vec y hat t plus 1 minus y vec is less than t minus y vec 2 norm minus eta times 3 over 4 sigma square. And then you can do a recursion to get exponential decay of error. Okay, any questions? I think I made a small typo somewhere in the assumption of the theorem. I need to fix that. I think my assumption should be that this is less than c over square root n. But it doesn't really matter because you can make beta and sigma if you change, as we see last time, right? If you make either the width bigger or the alpha bigger, you can make beta over sigma square arbitrarily small to small. So it doesn't really matter that much. Any questions? Sure. Yep.
Most here you don't have this exponential.
Mm-hmm.
You still can use the
So I guess, I think there's one version to, like, let me rephrase your question and let me know if it's not what you asked. So I guess one question you could ask is that whether you really rely on the exponential decay for the kernel case to have this relationship between your network and the kernel. I think the answer to that is no. So the second type of approach that I somewhat outlined last time but didn't really go into detail, that approach doesn't require that you have exponential decay of error. So in that case, both the kernel and the network, you can only show them to have some polynomial speed of decaying. Like the error is polynomially in T. So you can still make this relationship. So exponential decay is not that important. But I think this is actually something that people realized after the first few papers. At the very beginning, the very first paper using this exponential thing, and people thought that because you have exponential decay, you converge so fast, that's why you don't leave this neighborhood. But I think you can do something so that even without exponential decay, you still don't leave the neighborhood. Because whether you leave the neighborhood probably depends most on whether in the neighborhood there is a global minimum, right? If there is a global minimum in the neighborhood, but somehow you cannot converge to it exponentially fast, that's still probably fine as long as you converge to it eventually, right? So I'm not sure whether that's what you asked. Okay.
So I was just thinking, why would you care about it? They have similar optimization problems, but I think here you want to show that they kind of stay close to let's say inside the region.
Right. You do want to say, and also you want to, you want to characterize the networks, right? So if they don't have the same property, right? You somehow can analyze the optimization of networks, that's fine. But I think it becomes tricky. But the relationship is something to help us to bridge the gap between what we knew and what we don't know, right? So for networks is something we didn't know, but the kernel one is something we knew, and if they are similar, then you can hope to analyze the network, right? Yeah, so I think that's why we need to show they are doing something similar. Okay, all right. I think that's. I think I have a little bit more things to add about the neural tangent kernel. I guess we've discussed this many times. Like the limitation of neural tangent kernel is that you only, at most, do as well as the kernel method, right? So they are kind of. So basically, the question is, how well a kernel method can work. Right, so are we really characterizing the power of deep learning? Right, if deep learning is only doing as well as kernels, is it good or bad? Right, so and the answer I think is that, at least I think most people believe in this. The answer is that neural network can do much better things than kernels, and this characterization of the neural network as kernels is not characterizing the true power of neural network. And you can try to say this in various ways. So there are a lot of papers that tries to do this, right? So beyond the NTK approach, I guess if you search beyond NTK or beyond lazy training, you'll see a bunch of papers, including some of my papers. So we try to analyze deep learning in different regime. But there's a simple separation if you don't care about the optimization performance. If you just care about the power of the regularization if you only care about the statistical aspect, you can easily show that neural network can do better things than kernels. And this is a example. So the example is something like this. So I guess this is an example where NTK or any kernel method is statistically limited. So, and in some sense, the intuition is that the limitation comes from that the kernel or the features are fixed in the NTK approach. You don't have any adaptivity to the data. So your data probably wants to use some features, but you are using a fixed feature for your data. So and this is a simple case where you can have such a concrete example. So suppose you consider this case where x is in say RD and y is in +1 -1, and let's say each of the xi's are just a uniform, like a IID Gaussian. So xi is ith example, ith index. The superscript is for the examples, and the subscript is for the dimension. And let's say y is equals to x1, x2. So you have a very simple function, which is just learning the product of the first two dimensions of the data. So if you draw this, suppose this is x1, this is x2, then you just have 4 different combinations, and this is a positive example, this is a negative example, positive example, and this is negative, and this is negative. So this is not linearly separable because you have these 4 points that are positioned like this. So you have to use a nonlinear model or a linear model on some feature space, right? So if you use neural networks, and suppose you regularize the L2 norm, and this is equivalent to regularize this norm that we discussed, right? This norm C theta, which is something like sum of AI WI. I'm not sure whether you still remember this, right? So when we have this neural network, which is y is equals to something like sum of AI sigma WI transpose X, and you can define this complexity measure, which is the kind of like the path norm, right? And we have shown that regularizing L2 norm of the order parameters is the same as regularizing this somewhat complicated norm, which gives actually the complexity generalization guarantees, right? So we have discussed this, and in some sense, and suppose you use the neural networks, then what you'll find is so the best solution. By the best solution, I mean the minimum norm solution, the minimum norm solution is a sparse one, right? Uses a sparse combination of neurons. So basically, the best solution, actually, in this case, you can exactly compute what's the best solution. I'm not going to prove it, but I think it's something relatively believable. So the best solution, first of all, doesn't really use any other dimensions. That seems to be believable, right? Why you want to use any other dimensions if your function is only a function of the first 2 dimensions? And you only have to use something about the first 2 dimensions. You only need the following 4 neurons. So one neuron compute x1 plus x2, and another neuron compute minus x1 minus x2. And you need another neuron that computes value of x1 minus x2, and another one that computes value of x2 minus x1. So I claim that this is actually equals to the function. And if you want to verify that, I can briefly do that. So value of x, value of t plus value of minus t, this is equals to absolute value of t. So this is equals to x1 plus x2 minus x1 minus x2. And now I claim that this is actually equals to x1 times x2 when x1 and x2 are both binary. And how do you see this? I guess the only way I can see this is just to like try all the 4 combinations, right? If x1 and x2 have the same sign, then this will becomes 0 and this will becomes 1. Right? If x1 and x2 are either both 1 or both minus 1, and that is the case when x1 and x2 the product is 1. And if x1 and x2 have different sign, then the first term is 0 and the second term becomes 1. Wait, why I'm having a half here? Oh yes, and second term becomes 2, right? So and you multiply half, and you get minus 1, right? So good. So basically, if you use neural network and you regularize, you can show that this is the solution you find, which is a very sparse combination of a small number of features. In some sense, when you use regularization, you find these 4 features, and you do a linear combination on them. So these 4 features are the right features for this task. However, if you use NTK, suppose you use NTK, suppose you're using NTK, then what you do is you don't learn any features. You just try to do a L2. You do a dense combination of your existing features, right? So in some sense, what you do is you say, I guess how do I say this in the best way? So basically, when you do NTK, what you learn is something like sorry, why I'm not? I guess I can state a theorem, but I think roughly the intuition is that your prediction will be something like a sum of AI sigma Wi transpose x, or maybe something like this, sum of AI times phi of x, right? And there are a bunch of features, and each feature is phi, and these features use all the dimensions. This depends, of course, exactly what the features are depends on what kernels you are using. If you use kernel, you're going to get some feature vector. If you use random kernel, you get some other feature, some other features. But whatever features you do, this is always the function of all the data, right? So there's no, you cannot specialize to a special subset of features. And also, because you are doing a regularization on the minimum L2 norm solution for the coefficient in front of the feature, you don't prefer any sparse solution, right? So recall that yeah, sorry, I'm using the wrong version of notes, so I guess I have to improvise a little bit. So if you look at NTK, what you do is you try to minimize the L2 norm of this vector A such that the data sum of AI phi x is equals to y. Maybe we also have J. Right. So, and if you do the neural network, I think we have claimed that neural network is the same as L1 SVM in the kernel space. So then the corresponding thing would be you minimize the L1 norm of A such that the sum of AI phi xj is equals to yj. So in some sense, when you do the neural networks, you have a lot of features, and you're choosing a subset of features, a sparse subset of features. And when you do NTK, you are minimizing the L2 norm. That never gives you sparse combinations. It actually prefers dense combination. It's the reverse direction. You want as smooth combinations of the existing features as possible. So that's why you have to pay more samples if you use NTK, because you are using kind of suboptimal features. And this can be proved in this case. Like you can prove that this is a theorem where you can prove that kernel method with NTK kernel requires n to be omega of d square samples to learn a problem. With error less than 1. And in contrast, regularized network only need neural nets, only need n is equals to O of d samples. Any questions about this? I think this part is a little bit kind of like hand wavy because I didn't want to go into all the details. And also this depends a little bit on what we discussed in the past, right? So the L1 SVM connections to the connection between L1 and SVM and networks. Any questions? So I guess maybe just to wrap up this once again. So basically, if you do neural network with regularization, then we have shown that this is equivalent to doing L1 SVM in the feature space. You are trying to find the sparsest combination of features that fits your data, right? And in this particular example, it kind of sounds pretty intuitive that finding a sparse combination is useful because not all the features are equally useful, right? So these features we designed are much better features than a random feature. So, and that's why neural network with regularization could have good sample complexity. And on the other hand, when you do NTK kernel or most of the other kernels, so you are not trying to find a sparse combination of the features. You are trying to find a dense combination of the features because you are doing L2. You're finding the minimum L2 norm solution. And the features, and each of the feature is a function of all the data, all the coordinates of the data point. So the features are not that useful in some sense. There's a lot of noise in your features. You have to rely on averaging all the noise over multiple features to learn something. You can still learn something, but it's going to be less efficient. Right, I think that's the summary. Okay, so if there's no any further questions, I'm going to move on to the next topic, which is about implicit regularization effect. I'm not sure whether you still remember what we discussed in the mystery of the deep learning theory section. So I'm going to briefly repeat the kind of the high-level goal here. So the kind of the observation we had about the empirical deep learning is that we found that there are multiple global minima of training loss exist. And the optimizers have some preference, have some implicit preferences. And we have claimed that almost every aspect of the optimizers have some preferences. For example, if you use the particular initialization that enables NTK, then you have the NTK preferences. You are learning the NTK solution. And if you use some other initialization, you have some other preferences. And we have kind of concluded that if the NTK solution is the wrong preferences, right? So like you don't do much beyond a kernel method. You actually do exactly the same as kernel method. So basically that means you are finding the wrong global minimum that doesn't necessarily generalize, as well as other global minimum. So from now on, we're going to try to look at other global minima of this objective and see what other optimizers prefer. So if you use different optimizer, you may prefer a solution that is different from the NTK solution.
What do you mean by the NTK initialization?
Oh yeah, what does it mean? The NTK.
I had some number of initialized so that you end up taking
Right. So why I call it NTK initialization, right? So the NTK, so this is by NTK initialization, basically I mean the initialization under which you can prove the NTK result. So maybe specifically, I think last time we have two examples, right? So one example is maybe this example is
when the result we just worked on from the last from how to
right.
probably just
Right. So for example, I think just when you have the width thing, right? So like where there's something like here, I think we have this overparameterized model, we have this width, and we initialize with AI to be +1, -1, and WI to be this spherical Gaussian. And you can, for example, initialize something with something much smaller, right? And actually you should, right? If you really do the experiments and for this exact parameterization, you should initialize both either AI or WIs, like maybe a 1 meg, some like a square root n factor smaller. And then you're going to see much different empirical result. And actually, we have done this, in the paper. Many people have done this. Like it's relatively simple experiments. So here you can say that initialization is the culprit, right? So for the other case, I think when you change the parameterization to see the NTK regime, I think you can say the parameterization is the culprit. And also, even in this case, right? Even in this case, suppose you initialize the same as the NTK. Suppose you do stochastic within descent. You have sufficiently large stochastic. It doesn't have to be super large, but a little bit larger than 0. Then you will leave that initialization area. You're going to converge to some other places. So that's another way to leave the NTK regime. Right. So we are going to, in some sense, discuss these other kind of like ways to, basically what we're going to discuss next are either use initialization to leave the NTK or use stochasticity. And what else? You can also use the learning rate. The learning rate too. Learning rate is kind of almost the same as stochasticity, because if you have larger learning rate, in some sense, and you have SGD, then your stochasticity is bigger. Right. So right. So the first thing we're going to do is the effect from initialization, the implicit regularization effect from initialization. The first is this effect of initialization. And you will see that in certain cases, you can leave, we don't necessarily really care about leaving NTK. We really care about like having a better generalization, right? So that means you have to leave NTK, but you have to do probably more than that to get better generalization. So so this is what we're going to do this lecture, the next 15 minutes of this lecture and the next lecture, the effect of initialization. And I'm going to start with a simple case where you have overparameterized linear regression case. You need the overparameterization because you need, especially if you consider linear models, right? One of the important things is that you have to have multiple global minimum. Otherwise, there's no so-called implicit regularization effect, right? Because optimizers have to converge to global minimum. Right? You have to have multiple global minimums so that the optimizers can have a choice to choose between them. So that's why we need overparameterized regression, so that you have multiple global minimum. Actually, there's an infinite number of global minimum when you have overparameterization. So, and we'll see that in this case, small initialization prefers low norm solution. And this is also the case when in the next lecture, we're going to go beyond linear model. And the high level conclusion is the same. If you use small initialization, then you prefer lower norm solution. So, and today we're only going to, in the next 15 minutes, we're only going to do the linear models. So, and this is actually not that hard. So let's set up first. So this is a standard linear regression case. You have something like, I guess for this lecture, I'm using the lower subscript for the number of examples, just because you should really look up any linear regression book, then they use subscript for examples. So And here we don't have so this. So each of these xi's are examples. Example I, and you put them into a matrix. And let's assume X is full rank. So means rank n. And let's also assume n is much smaller than d. Okay, so and we have a parameter beta. So you get a loss function y vec minus x beta 2 norm square. Let's say I have a half here just for convenience. This is my empirical loss. Okay, so this is standard linear regression. And indeed, L hat beta has infinite number of global mean. And it actually can characterize exactly what the global means are. And all the global means with error with loss 0. So what are the global means? So beta is equals to, suppose you take beta to be x pseudo inverse times y vec plus some vector zeta, where zeta is any vector that is also orthogonal to x1 up to xn, is a global mean. So as long as your beta has this form, then it's a global mean, and these are actually all the global mean. So, and actually here, I think last time someone asked about pseudo inverse. Maybe let me have some basic properties of pseudo inverse. I guess my way of thinking about it is probably slightly different from the Wikipedia. So the way I always think about pseudo inverse is the following. So I always think about it when there's in the SVD, because with the SVD I can verify everything, so that I don't have to remember them. So suppose you have a matrix X in dimension n by d, and suppose X is of rank R. Of course, R has to be less than either n, both less than n and less than d. So the way how I remember every property of the pseudo inverse is the following. So I consider X as SVD of X, which is U sigma V transpose, and sigma is of dimension R by R. Let's say you ignore all the non-zero entries. So and U is of dimension, say n by R, and V is of dimension d by R. So then you know that the column span of U is the same as the column span of X, and the row span, the column span of V, because there's a transpose here, right? So column span of V is the row span of X. And also you know that the pseudo inverse in this notation is, you can think of it as defined to be V sigma inverse U transpose. So here all the sigma, so here sigma is a diagonal matrix with entry sigma 1 up to sigma R, and sigma i's are all positive. So then this inverse is well defined, and X pseudo inverse is just this, V sigma inverse U transpose. And now if you want to understand what's the property of the pseudo inverse, you can verify it yourself. So you know X pseudo inverse, this is gonna be what? This is gonna be U sigma V transpose V sigma inverse U transpose. V transpose V is identity. So U transpose, right? Because V transpose V is identity, sigma times sigma inverse is identity. So what is this? This is the projection to the column span of X. Right? It's the projection to the column span of U, and the column span of U is the same as the column span of X. And X pseudo inverse times X, this is equal, if you do the same calculation, it's going to be equals to V sigma inverse U transpose times U sigma V transpose, which is VV transpose, which is the projection to the row span of X. And you can also see the dimension matches because this is a matrix of dimension d by d, and V, and the rows of V is in dimension d. Sorry, the rows of X is in dimension d, the columns of V is in dimension d. So right, and in the case when you have in this case where X is in n by d, then you know, and the rank is n, then you know that x to the inverse is the projection to the column span of X, and the column span of X now is the full span of all the vectors. Wait, column span is right. The column span is the span of the right. It's all the vectors. So that's why this is just identity. And X pseudo inverse X, this is the projection of row span of X. So how many rows there are? There are n rows of X, and they don't span everything because the dimension d is bigger. So you cannot span everything. So that's why this is not identity. This is really just the projection of the row span of X. You cannot simplify more. Right. Okay. So it's a little bit too long, I guess, as a building block. But okay, I hope this helps. Like, this is how I understand this pseudo inverse. Like, I never remember what x pseudo inverse is equals to. So this is how I remember. So and the question, okay, so now we have so many global minima, right? So, and okay, I think with this it's easy to verify these are global minimum, because you can verify this beta is global minimum because you can say take x beta, which is equals to x pseudo inverse y vac plus x zeta. The zeta is orthogonal to the rows of X. So that's why x zeta is 0. So you get x pseudo inverse y vac. And x pseudo inverse in this case is an identity. So you get y vac. Right? I just claimed that x pseudo inverse is identity. Okay, so that's why x beta is equal to y vac. That's why it's a global minimum. And the question is which global minimum you're going to converge to. So my theorem is that if you initialize, so gradient descent on L hat beta with initialization, beta 0 is equals to 0, and sufficient small learning rate. Learning rate. Actually, you know exactly how small it is. Like, I just don't want to give you too much jargon. So if you have learning rate small enough and the initialization is 0, then this converges to the minimum norm solution. So the minimum norm solution beta hat is defined to be the one among all global minimum where the minimum norm solution among all global minimum of the loss function. So basically you get this 2 norm for free, right? You're minimizing this. You didn't say that I want to have the minimum norm solution. You just say I want to do gradient descent, but you get the minimum norm solution for free. And the reason why you got it is because you express your implicit preferences through the initialization. Okay, cool. So yeah, I think I have 5 minutes, which is perfect for the proof sketch. So I guess this is actually really a proof, but I just I think I ignore some small details. That's why I call it a sketch. So the first step is that if you do standard convex optimization, you know that this goes to 0 as t goes to infinity, right? You know that if you run for a long time, then your loss will become 0. That's, you know, I'm not going to show how do you do this, but this is you can invoke any off-the-shelf optimization result. And the second thing is that you know that this beta hat is actually equals to x dagger x pseudo inverse times y back, right? So we know that all of these are global minimum, but if you take zeta to be 0, then that's the if you take, sorry, I think I'm, yes, if you take zeta to be 0, then that's the minimum norm solution. I think this is this. There's no x here. And this can also be simply verified, because if you take any beta, so for any zeta orthogonal to x1 up to xn, then you look at x pseudo inverse y back plus zeta, the 2 norm of this. This is equals to x pseudo inverse y back 2 norm plus zeta 2 norm plus 2 times x pseudo inverse y back zeta. And this is larger than x pseudo inverse y back 2 norm square plus 0, because the norm is less than 0. And this quantity is just equals to 0. Because, see why this is equals to 0. This is equals to 0 because I guess this is, maybe let's say this is equals to 2 times y back x. So what's this? This is zeta transpose x pseudo inverse y back, right? And I claim that this is equals to x pseudo inverse y back 2 norm. Because this is 0, and why this is 0, I guess this is actually a good way to practice what I had. So x pseudo inverse is v sigma inverse u transpose. Sorry, pseudo inverse is v sigma inverse u transpose. So the column span of x pseudo inverse is the same as the row span of x, right? So, and zeta, okay, sorry, this is transpose, not this. Zeta is orthogonal to the rows of x, so which means that zeta is orthogonal to the column of x pseudo inverse, right? So that's why zeta times this is the zeta times the columns of the pseudo inverse. So that's why everything is 0, right? So this is 0. So zeta is orthogonal to column span of x pseudo inverse, which is equals to the row span of x. Right. Okay, all right. So basically, you see that the norm is only decreasing if you set a zeta to be 0. That's why when zeta is 0, that's the minimum norm solution. Right. So 3, I guess this 1 and 2 are basic facts about this linear regression thing. The 3 is what's really about the optimization. So you can prove that beta t is in the span of x1 up to xn. You can prove this inductively. And why this is the case? This is a super simple induction, because beta t is equals to beta t plus 1 is equals to beta t minus eta times the gradient, and beta t, and what's the gradient? The gradient is x transpose y vac minus x beta. So this is in the column span of x transpose, and so it's also in the row span of x, right? So basically, your update is always in the row span of x. That's why you never leave the span, right? So, and beta, by the way, beta. So maybe I should start with the beta 0 is in this span. Beta 0 is in the span of x1 up to xn, and each time you update, and that update is in the span of x1 up to xn. So by induction, you get that you're always in the span. So basically, then, because you are always in the span, right? So the only solution to L hat beta 0 in the span is this, right? Because what are the solutions with error 0? The solutions with error 0 are these ones. I guess are these ones, right? So this has solution 0, and among this, who are in the span of the row span of X, right? So only this one is in the row span of X, because all of these are not in the row span of X. They are orthogonal to the row spans of X. So the only solution that is in the row spans of X is just the first term. We just take the first term. So, and that happens to be the minimum norm solution, and that's why you get a minimum norm solution. In some sense, basically all the magic come from this, right? So basically, this is a regularization in some sense. This is a constraint imposed by the algorithm. The algorithm say that you cannot go everywhere. The algorithm say you can only go to those places where in the span of the data. So that's why you have to stay in the span of the data, and it happens that in the span of the data, there's only one solution, and that solution is the minimum norm solution. Right. So I think, in some sense, if I draw a picture, okay, I guess I'm running late, but real quick. So if I draw a picture, I think this is a very difficult picture to draw, but I think you can still try it. So if you have you can have maybe let's say this blue direction. This is the span of the data. Let's say suppose we only have sometimes one data, so the direction of the span of the data is only one dimensional. And then you have a subspace of solutions which are orthogonal. So this is orthogonal here to the span, right? This is the solution where you have this, right? So it's orthogonal to the span of the data, and the intersection part is the target solution. So the intersection, the intersection part is really X to the inverse Y back. And so you start with this. You try to reach this purple plane, because that's the optimization wants to do. The optimization wants to reach the purple plane. But optimization also say you can only go in the blue direction. And so that's why you meet in the intersection. And the intersection is the closest point to the origin. Okay, I guess that's all. Yeah. Yeah, so do you need a condition that you have to span on a span, right? So yes, you do, because if you don't span, suppose, for example, what you suppose to start here. So what happens is that you can only move in this direction. That's what the algorithm says, right? The algorithm says the update is in the span, so you can only, all your changes is in the span, so you can only move. So basically, you go in this way until you hit here. So then this place is not a minimum norm solution anymore. This place is going to have some higher norm than the ideal point. Yes, so you can say the implicit regularization effect always happens, but the effect is in the minimum norm solution only if your initialization is 0. Like you always have a preferences, right? So whatever you do with initialization, you have some preferences about which global minima you want to converge to, right? But if you want the preferences to be the minimum norm solution, then you really have to choose 0 as the initialization. Any other questions?
Do we have any hope of this kind of argument? I guess what this, like this is sort of saying if you take D back down to N, you'll still be able to solve. Like, there's some solution.
Right.
Is this going to, or is it going to map nicely onto the nonlinear cases, or are we going to need a new definition?
Right. So the question is whether there's any hope that this can transfer to nonlinear cases. I think here we are using a lot of things about linear algebra, right? So we know what is the minimum norm solution, so on and so forth. We have the orthogonality, everything, right? So when you have nonlinearity, you don't have most of this. So those parts that we discussed about the very heavily linear algebraic part, those don't transfer at all probably. But somehow at least we can find one other situation where when you have nonlinear models, you can still do, you still prefer the minimum norm solution, and that's next lecture. Yeah. So, but the mechanism is somewhat, it's not exactly the same. So next lecture and this lecture, the only connections is that the final message are similar, or the same, but the techniques are quite different. We still don't know how to unify them in the right way.
Seems to relate it to like a fluid approximation.
A fluid?
Fluid approximation, so different approximation. So you can use a GDS or traveling on different equations.
Right.
Yeah, and yeah, I'm wondering if like, in nonlinear cases you can do something, or have some thing like you can learn with it small and roughly to different equations.
Yeah. So you're absolutely right. So like the difficult case come from the very, very small linear rate case. I think infinitesimal small linear rate case. So even for infinitesimal small linear rate, so basically you have a differential equation, right? You just have a trajectory, and you want to know where the trajectory goes, right? So as far as I know, like I'm not I don't know too much about differential equations, but I think the problem is how to solve that equation. Like you know the solution exists, you know there's a trajectory, but where the trajectory really goes, that's the hard part. I don't think at least I'm not aware of any papers that use tools from differential equations heavily, right? So this is a useful language, right? So you can, from the language, like the formulation of the language perspective, the differential equations language are very useful. But typically the hard part is how to solve it. In some cases you can. I think I know one paper where you can solve it, but it's not like it's using the structure of the problem. You have to literally solve it using some new math. It's not like you can invoke a theorem in the differential equation literature, say these kind of questions can all be solved. I don't think so. Okay, sounds great. Okay, cool. See you next week.